So in section 6.2, we are adding to our integration toolbox so that we can begin to integrate more functions than just with the basic rules that we looked at in 6.1, which were if you integrate a constant, it's equal to the constant times x plus c. If you integrate, say, x raised to the n power with respect to x, that would be 1 over n plus 1 times x to the n plus 1 plus c. If you integrate 1 over x with respect to x, that's natural log of the absolute value of x plus c. So in this case here, n cannot be equal to -1. When n is equal to -1, that's when the integral is equal to the natural log of the absolute value of x plus c. And then the integral of e to the x with respect to x is just e to the x plus c. So we have these basic rules of integration, and we're going to still be using those, but now we're also going to be using something called u substitution. So if we look at these integrals, you would be trying to integrate these more complicated looking functions that are maybe products or quotients or raised to kind of a more complicated power than just x, and we don't have any we don't have any product or quotient rules for integration. So to be able to integrate these integrals, we would have to use integration by substitution, which is also known as u substitution. Okay, so here's our substitution rule, and really here, g of x is u, and g prime of x dx is du. So we're essentially trying to let u equal to some piece of the function that you're trying to integrate so that you can write your integral in a simpler form that you can integrate using those basic rules of integration. So for this one, we would want to let u equal to x plus 2. And then we're going to take the derivative of u with respect to x. So this is the same thing as like before. If you had the equation y equals to x plus 2 and you found the derivative, that was dy over dx was 1. So we're doing the same thing now. It's just that we're using u instead of y. So we're going to differentiate u with respect to x, which is du over dx, which is 1. So now our goal is to isolate dx. So I'm going to multiply by dx on each side of the equation. Okay, so now that I've done this, I'm going to rewrite the integral, where I'm replacing x plus 2 with u, so I'll have u cubed. And now dx is equal to du, so I can actually replace the dx with du. And this is a function that I can integrate. This is going to run into this, so I'm going to move this. But I can just use power rule, and I would get 1/4 u to the 4th plus c. And then to finish, I can just substitute the x plus 2 back in for u. And remember that you can always check that you have integrated correctly, that you've found the correct antiderivative by taking the derivative. So to take the derivative of this first piece here, we would think chain rule. So 4 times 1/4 is just 1. We leave the inside alone. Now raised to the 3rd power times the derivative of the inside, which is just 1. And then the derivative of c is equal to 0. So we can see that our derivative matches the function that we just integrated. Therefore, we integrated correctly. We found the correct general antiderivative for this function, which is the 1/4 times the quantity x plus 2 to the fourth plus c. Okay, sometimes it can be a little tricky, and with practice you get better at determining what you want to let u equal to, but sometimes it's a little bit of trial and error, and u substitution doesn't always work. So for this one, I'm going to let u equal to x cubed minus 1. Then I take the derivative of u with respect to x to get 3x squared. So same process as last time, I'm going to isolate dx. So I'm going to multiply by dx on each side of the equation. And then I can divide by 3x squared. So we get du over 3x squared is equal to dx. So now I can substitute u in for the x cubed minus 1 and replace dx with du over 3x squared. Now this is good because our x squareds will actually be able to cancel, and then 3 goes into 6 2 times. So this ends up being the integral of 2. I'm going to rewrite the square root of u as u to the 1/2 du. And you do have the option of pulling the constant out front. But this is something I can integrate now with power rule. So I would have 2 times 1 over 1/2 plus 1 times u to the 1/2 plus 1 plus c. And in simplifying that, I would end up with 1 over 3/2, which is 2/3, and then 2/3 times 2 would be 4/3, times u to the 3/2 plus c. And to finish, I can substitute x cubed minus 1 back in for u. Okay, so for this guy, I'm going to let u equal to 2t squared plus 5. Find du over dt, which would be 4t. So that's just the derivative of u with respect to t. Now we're trying to isolate dt. Divide by 4t on each side. So we get du over 4t equals 2 dt. Solve the integral of t over u, du over 4t. So now the t's will cancel, and I'll actually have a 1/4, constant 1/4 that I can pull out front of the integral. And I know how to integrate 1 over u is the natural log of the absolute value of u plus c. And then we can substitute the 2t squared plus 5 back in for u. Okay, so I want to let u equal to 1 minus 4x. Du over dx would be negative 4. So we get du equals to negative 4 dx, and then I can divide by negative 4. I'm going to rewrite the cube root as u to the 1/3. Then we have du over negative 4. So I can pull, there's nothing to cancel here, but I can pull that negative 1/4 up front of the integral before I actually integrate. So then just using power rule, I'll have 1 over 1/3 plus 1 times u to the 1/3 plus 1 plus c. Remember, as soon as you integrate, you drop the integral symbol in your du or your dx, and you add c. So this will end up simplifying to be -3/16 times u to the 4/3 plus c, and I can substitute 1 minus 4x back in for u. And remember, you can always check by taking the derivative of what you get for the general antiderivative, and it should match the integrand. Okay, so let's try letting u equal to 3x squared minus 2. And then isolating dx. We'll have the integral of 4x times e to the u du over 6x. So basically we want to be able to cancel whatever variable we have not let u equal to, or whatever part of the function we have not let u equal to. We want any remaining x's to cancel. So this will be 2/3 times the integral of e to the u du, right? Because 4/6 is 2/3. So that will just be 2/3 e to the u plus c. And we're done. This one I would let u equal to x cubed plus 4. And I want to use x cubed plus 4 because I know that the derivative of x cubed will give me x. I'll have an x squared that can cancel with that x squared. So I'll have du over dx equals to 3x squared. Dividing by 3x squared on each side of the equation to isolate dx. So we'll have 9x squared over u to the 6 du over 3x squared. This is good. The x squareds cancel. 3 goes into 9 3 times. So I can pull the 3 up front, and that'll be 1 over u to the 6 du, which I'm going to rewrite that as the integral of u to the -6 du, so that I can use power rule. So that would be 3 times 1 over -5 u to the -5th plus c. So -3 over 5u to the 5th plus c. And then I can substitute x cubed plus 4 back in for u. Okay, I'll leave the u try for you guys. Just to get you started, I would probably let u equal to x cubed plus 1. Okay, sometimes it's not as obvious. Like I know in class, everybody said to let u equal to 4x at first, and then du over dx is equal to 4. So you end up with du over 4 equals to dx. But the thing is, then when you substitute the u in, you still have this natural log of u over x, and then du over 4. Well, you still have an x in there, and you're integrating with respect to u, so you get stuck. So we have to, in that case, if that happens, you want to look at, is there anything else that you could let u equal to? So let's try letting u equal to the entire numerator of natural log of 4x. So du over dx would be 1 over 4x times 4, thinking chain rule, which is just 1 over x. So du equals to dx over x, which if you see it, that is what's in the integral, the original integral. So you could actually just stop there and say, oh, well, that's du. So the integral of natural log of u, sorry, not natural log of u, sorry. You would have u du, right? Because we let u equal to the natural log of 4x, and then du is dx over x. If you don't see that, that's okay, and you can always just isolate dx like we've been doing, and then we would have u over x times x du, and then you see that the x's will end up canceling. So you end up integrating u du using power rule. Okay, don't forget to substitute whatever you let u equal to in the beginning back in at the end. So u substitution is useful for letting u equal to the exponent in an exponential function if necessary, an expression that's in parentheses, a complicated denominator, or we just used a numerator, or an expression that's under a radical sign. But remember, not all functions can be integrated with the rules we're now familiar with. So there's some other methods that you might learn in future calculus courses, or you might even need technology. Okay, so you'll see here's an example of a function that you're actually not able to integrate using u substitution. So we actually could integrate this function by hand, but we would have to multiply out x squared plus 4 to the 7th power, because this is a polynomial just in factored form. So you would have to multiply it out, and that would just be ridiculous to do by hand. If we try u substitution, we would probably want to let u equal to x squared plus 4. So du over dx is equal to 2x. Du equals to 2x dx, du over 2x equals to dx. But we get stuck because we have this x here that's not going to cancel with anything. You look at the function, you go, oh, is there anything else you could let u equal to that could possibly work? And there's not. So this function, the only way that you could do it is by expanding